Continuing on with the solution of this problem involving the water bridge. What's the pressure at the bottom of the aquarium? Well, what we have to work with is the delta P equals rho Gh. So here, relative to just atmospheric pressure at sea level, we're assuming this aquarium is sort of near where we are, we've gone down 20 centimeters in the fluid, so that H is 20 centimeters or 0.2 meters. So what I'm going to do is say if the change in pressure is equal to rho Gh, that means the pressure at the bottom is equal to the pressure at the top of the fluid. That's atmospheric pressure, 101.3 kilopascals, or 1.013 times 10 to the 5th pascals, plus the change in pressure from the top to the bottom. That's rho Gh. Rho is 1,000 for water in SI units. G is 9.8. and H is 20 centimeters or 0.2 meters. Putting all that together, we get 1.033 times 10 to the 5th. So notice it's a little bit bigger by, a couple percent or something like that, larger. It doesn't go up by a huge amount compared to atmospheric pressure. What's the pressure at the very top of the water bridge tube, which is, by the way, 12 centimeters above the surface of the fluid. So to get from the surface of the fluid, that's atmospheric pressure, right, up to the top, we have to put in H equals minus 12 centimeters or minus 0.12 meters, right? Because to get there, we start at the surface and we have net gone up by 12 centimeters. So we have atmospheric pressure plus rho Gh, and our H is minus 0.12 here. So that gives us something a little bit less than atmospheric pressure. So I don't know if the fish maybe don't like that so much. They're not used to being at pressures that are ever less than atmospheric pressure. The pressure goes down a little bit as they go up there. Who knows what that feels like to them. To us, we notice that, if you've been down at the at lower elevations and you drive up to higher elevations, sometimes your ears pop as fluid comes out of the inner part of your ears. So maybe they have an analogous effect. What is the gauge pressure at the very top of the water bridge tube? The only difference between gauge pressure and absolute pressure is that in gauge pressure, we don't add on atmospheric pressure on top of it. So the gauge pressure in this case is actually negative up there. It's just this second term being added on there. Minus 1176 pascals. Speaking of Pascal, one of the next topics that you read about is called Pascal's principle, and it says if you have some fluid that's confined to some sort of container, in other words, it's not open to the atmosphere perhaps, and you apply some additional pressure to it, maybe you've got some kind of plunger or sort of piston thing where you can apply additional pressure to the fluid. The pressure at every point within the fluid increases by the same amount. Okay, so we can imagine, just to see what it means here, we can imagine here's our graduated cylinder open to the atmosphere, partially filled up with fluid. We put a piston on the top of it, which is sealed, so it makes a nice seal with the glass there. And then we push down with a force on top of the piston. So we're applying additional pressure on top of this. Before it was just atmospheric pressure. Now we're adding some pressure on top of that to increase it. And I'm just imagining here, maybe up above, of course, nothing changes because we're still open to the atmosphere there. But down in the fluid, just below the piston, it's gone up by a certain number of pascals. And all of them, I'm imagining here, went up by, it looks like up by 100 kilopascals everywhere. So that's Pascal's principle, is that the pressure goes up by the same amount everywhere in the fluid when we apply some additional force to it like that. One of the applications is that, one of the applications to this is to use hydraulic systems which just are able to transfer force from one plunger to some other kinds of plungers. So here we're imagining if you push inward on this particular cylinder here, you force fluid through this tube, and that forces it into these cavities down here, and they're going to push these cylinder things outward, and we might be able to use that. In fact, we can use that and do use that in disc brakes in cars. So that was just a blow up of this picture here, where the brake pedal compresses the fluid in here, and then there's an enclosed system where the only thing it can do is push against these movable brake pads that are on the edge here. And when you push on that, you increase the pressure that pushes inward on the brake pads, and that causes them to squeeze the disc, which is attached to the wheel, and that causes your car to slow down. So it's just a convenient way to transfer some force that you're pushing on at some location to some other location. It's also used in hydraulic lifts, for example. When you, if you have a car over here, you might think, how the heck am I going to lift a car? A car weighs a ton, but you can actually lift a car using just your finger if you construct this the same way. So the idea is that when I push down on the fluid, the pressure increases by the same amount, and therefore, before we ever applied any pressure, the pressure at the same heights was the same, right? Because as I go from right here downward, it increases, going to the left, it stays the same, and then it decreases by the same amount going up there. So the pressure was the same. If I now have some additional pressure over here, we have the same additional pressure over there, and so I can still transfer forces between the two. But if the pressures are the same, that doesn't mean the forces are the same, because if pressure is force divided by area, that means force is pressure times area. If I've got a bigger area of this cylinder over here and a smaller area over here, I can actually increase the amount of force. I can push down with 10 newtons over here, and maybe it pushes up the car with 100 newtons over there, and so on. Or I can balance the car just by pushing downward with that amount. So let's do a problem associated with this. How hard would you have to push down on a piston over here at this location, Fn? Same picture that I just did, it's sort of grainy here. How hard would you have to push on the cylinder, which has a radius of 1 centimeter, to lift a car that has a weight of 10,000 newtons sitting on a cylinder of radius 1 meter over there? So let's do the calculation. The idea is, before we ever applied anything, the pressure was the same at the same heights. Now the pressure is also going to be the same at the same heights. It's just going to have increased by the same amount. So that means the pressure here is equal to the pressure over there. That doesn't sound very exciting, but we're not interested in the pressures. We're interested in the forces. So the fact that the pressures are equal because they're at the same heights in the fluid means the force that I have to apply down here divided by the area of that cylinder is equal to the force being applied down by the car's weight times the area of this cylinder. And let's follow that through to its consequences. How hard do I have to push F in if F out is 10,000 newtons? And when I do that, I have different radii for the cylinders there. In order to hold up a 10,000 newton car in this situation, I only have to push down with about 1 newton force. And if I want to lift the car, of course, I just push down with, once I've got it accelerated a little bit, I still just have to push down with 1 newton of force. And the car will be lifted, that 10,000 newton car. Seems like you're getting something for free. You're not really getting something for free. This is what's called mechanical advantage. It's the same way you can lift a big heavy rock by using a lever. In this case, we're able to lift something heavy on this side with a small force over here. The idea is, in whatever work we have to do to lift the car, that's the same as the work that's being done over here. So you're not getting any energy for free. But in order to move the car upward by a tiny little bit, you would have to move this plunger down by quite a bit. So the works done are actually the same. But still, it's kind of amazing. One of the things we didn't get to do this semester in the lab that I really wanted to do is play with this kind of stuff in the lab, because when you play with different plungers of different diameters, it's really striking how much, how hard it is to lift up things on one side and how easy it gets when you push down on the other side. All right, let's talk about the buoyant force. You have some intuition about what we call the buoyant force. For example, if we float a beach ball on the surface of water, we know the Earth is pulling down with the weight of the beach ball. There's got to be something pushing back up if it's just sitting there and not accelerating downward. What is that force? Well, it's a force upward from the fluid, and we call it the buoyant force, and they must balance out because this ball, we're imagining here, it's just floating freely. It's not going anywhere, and so those two forces must balance. If you come along and try to force the beach ball under the water, the buoyant force actually increases. And so we want to figure out the nature of this buoyant force. The buoyant force is the thing that tries to buoy things up, or it's an upward force from a fluid. Just in terms of how to think about the buoyant force, the relative size of the buoyant force and the weight determine whether things float or sink in the water. For example, if we have the beach ball, if the thing is totally submerged, the buoyant force might be huge and the weight is somewhat small. So that means the ball is going to want to start rising to the surface. In other cases, if I have a block of aluminum or something, there's still a buoyant force, but the weight in that case might be bigger than the buoyant force, and that's going to cause them to sink. So whether something wants to float, or sink when you put it in water depends on how big the buoyant force is compared to the weight when it's submerged. What's causing the buoyant force? I mean, it seems a little bit confusing or mysterious when you first hear about it, but there's nothing mysterious about it at all if you understand pressure and the properties of pressure that we had before. First of all, the pressure is it's increasing as we go down in the fluid. And on the surface, I'm imagining here's a ball that's submerged. The pressure, we said one of our properties of pressure is that it always pushes in the direction perpendicular to the surface. So if I drew sort of qualitatively what the pressure is, or the little bits of force being applied to the surface of the ball, they would look like this around the surface of the ball, right? The pressure is not as big up here, so on this little patch up here we have a smaller force, whereas in the same size patch down here we would have a bigger upward force. And same thing for all these arrows. They're sort of getting smaller as you go up because the pressure is decreasing as you go up vertically in the fluid. And so because the left and right components of those vectors cancel, but the vertical components don't, right? I've got more upward force than I do downward force. And that's the source of the buoyant force. It's just the fact that pressure increases as you go down in the fluid. So the fluid's pushing more up on the bottom of the object than it is pushing down on the top. And so the object tends to want to go upward. All that's due to the drumming of the molecules down at the molecular scale. If we want to do something quantitative to figure out the buoyant force, we could first do it in a simpler case because, with a sphere at least, it's somewhat confusing. So what I'm going to do is take here a cylinder. I think this is copied from Giancoli's book. A cylinder with the top and the bottom parallel to the surface of the fluid here. So let's assume the top of the cylinder is at height h1, bottom is at height h2. The cylinder has a cross-sectional area A, and there's a difference in height between the top and the bottom of delta H. And of course, we're expecting there's a smaller force on top and a larger force on the bottom. And so the buoyant force is just the difference between those two forces. And that's because, yes, there's also forces pushing inward on the cylinder from the sides, but those aren't trying to float it up or down. They sort of cancel on the left and on the right and on the front and on the back symmetrically. But the top and the bottom forces don't cancel. So those are the ones I want to get a handle on for the buoyant force. So I will call those F2 and F1. The buoyant force is the difference between those. Writing those forces in terms of the force on the surface, that's going to be the pressure at this height h. So if we're at h1 here, the pressure is rho Gh1. So that's rho Gh1. So the pressure is rho Gh1. Pressure times area is the force. So this represents the force on the top. And rho Gh2 is the pressure on the bottom. And if we multiply that by the area, pressure times area is force. This is the force on the bottom. We've got some things that we can factor out in common. In fact, the only thing that isn't the same is the H2 minus H1. So H2 minus H1 is what's defined as delta H over here. And if we then think about the geometry of this, the volume of this cylinder is nothing but the area times delta H. So A times delta H is the volume of the cylinder. So in this case, the buoyant force is equal to rho times G times V. And we can also think of rho times V, that's mass per unit volume times volume, is the mass of the fluid, right? If we're taking this, if this rho is the rho of the fluid, that's how we used it up here. Rho times V is the weight of the fluid that would have fit in the same volume as this object. So I've got maybe a brass cylinder under here, but this rho times V is the mass of water that would fit in that same volume if we're using rho as the rho of water. Okay, so sometimes people say the weight of the fluid displaced. That means when you push that cylinder underneath the fluid, a certain amount of fluid is pushed out of the way by the virtue of the fact that it's there. And so in this case, what we found out is the buoyant force equals the weight of the fluid displaced. That's called Archimedes' principle. This is the source of the eureka moment of Archimedes, when supposedly he was sitting in the bath and sort of had the reasoning in his mind to figure out that it was the weight of the fluid that he pushed out of the way, which is the additional buoyant force, which is the reason why you feel lighter when you're in water, right? When you sit down in a pool, you actually feel like you're not as heavy, right? And in fact, if you get completely submerged, you're almost don't have any weight at all. It just depends on how much air you're holding in your lungs. And that's because the more of you that's in the pool, the further down you go, which means you have a larger pressure down by your feet, and also the more of you has a force pushing up on it too. So all of that is the buoyant force. So Archimedes' principle says the buoyant force on an object immersed in a fluid is equal to the weight of the fluid displaced by that object. And it's also true if an object is only partially in a fluid. If it's partially submerged, you just look at the amount of fluid that's pushed out of the way by the part that's underneath the water, and that would be the partial buoyant force in that case. So in this case, what we do, we think about it, I guess a sort of a derivation of this. It's, that the argument we made before was sort of special to that cylindrical shaped object, but here's the argument in general. If I want to figure out what the buoyant force is, let's imagine I've got some object. It doesn't have the same density as water, so maybe it would sink or something like that. But I have the idea of this pressure around the outside of it. In order to get some intuition about it, I could imagine taking just pure water in the container and imagining the pressure on that volume of water that's sitting in a bunch of other water here. The pressure on the outside of that spherical volume of water would be exactly the same because we're at the same depth in the fluid in the left and right cases. The only difference is if this thing's really massive or if it's really light like a beach ball, it wouldn't be in equilibrium. Whereas in this case, this piece of water, the spherical volume of water, is in equilibrium. It doesn't want to go up or down. And therefore, the weight of the water must equal the buoyant force, right? If it's in equilibrium, the sum of the vertical forces must be zero. It's got its weight going down, and what's pushing up on it? The buoyant force. Since it's in equilibrium, those two must balance. The buoyant force in this case is exactly the same as the buoyant force over here because the pressure is the same everywhere on the outside of the volumes in those two cases. So therefore, the buoyant force is equal to the weight of the water that must have gotten pushed out of the way. That's the derivation or sort of intuitive idea of how to think about Archimedes' principle. All right, let's do the next problem. I think this might be labeled as problem 3 on the worksheet, but in any case, we've got ice of given density. It's a little bit less dense than water. That's why ice floats on the surface a little bit above the surface. So if we have a cube of ice, perfect cube, 2.5 centimeters on each side, place it in water, how far above the surface of the water does the ice cube stick out? It floats just a little bit above the surface. We want to calculate that. Okay, looks like I'm taking a break here. I didn't realize I was stopping, but we'll be back.